Hey everyone, in this video we're going to talk about the derivative as a function. So in the previous video we talked about derivatives, but only at a particular point C, which is the same as finding the slope of a tangent line. This time we're going to generalize the formula for any point x along the curve. This is very important because when we study derivatives, we rarely are interested in just one point. We usually want to study the function as a whole and the derivative along all of the points, which is why we do the formula in general. What we're going to do is we're going to find the derivative for any x, and then after we have the derivative for x in general, we can plug in whatever x value we want and talk about any point along the curve. So that's what this formula is going to do here. So again, the difference quotient here is the formula for the slope of a secant if you plug in a particular x value. And then you take the limit, which turns the slope of the secant into the slope of the tangent, because the secant lines approach the tangent line as h goes to 0. But by leaving it as x in general, we're now finding f prime of x, a general derivative of the function f. Okay, so this is our formula, or a function that we're going to consider using here. Notice they don't give us a point, they just have us find the derivative in general. Let's write down our formula. I always like to copy the formula. It helps me remember it by repeating it, by writing it every single time I do a problem. So we have the limit as h, as h goes to 0 for our difference quotient f of x plus h minus f of x all over h. So to do this formula, just like before, you need to first find f of x plus h. I like to do it on the side. You can do it in the problem if you want, but I tend to find it easier to do the extra algebra on the side of my problem. So here's my function f. I need f of x plus h. Literally that means plug x plus h in for the x. So I'm going to have x plus h, and then it was squared, my x, so I'm going to square the whole thing, x plus h all squared, plus 3. Now, we've talked about this before. What does it mean when you have a parenthesis squared? It literally means you need to multiply the parenthesis times itself. So I'm going to write that out. All right, let's FOIL. X plus h times x plus h is x squared plus xh and another xh, so 2xh. H times h squared plus 3. I can't simplify that any further, so this is what I'm going to plug in to my derivative formula. So don't forget your limit notation. Keep that until you actually take the limit. We're going to plug what we just found in for f of x plus h. Just copy it over. I'm going to put parentheses around that just to help me know that that is only the first piece of my formula. The formula then says minus f of x. Well, f of x is the original function, so I just have to copy that down. I'm going to put it in parentheses because I have to. Why do I have to have parentheses there? Because it's minus the whole function. So the parentheses is how you make the negative distribute to the whole function. H is still h until you take the limit, so the bottom stays the same. At this point, you're going to simplify. Remember, this minus sign distributes here. So you can write the step where you distribute it, or you can remember it's always a minus whatever's in the parentheses. For example, we have x squared out front minus x squared, so those cancel. And we have a 3 minus a 3. So if we write what's left, limit as h goes to 0, what survives? 2xh plus h squared all over h. Okay, you could try and plug in 0, but you're going to get 0 over 0. So you got to continue doing the algebra simplifying. So every single term has an h. You can factor the h out of the top or just reduce every single term by an h. So we have here the limit as h goes to 0 of 2x plus h. Let h go to 0. If h goes to 0, all that survives is the 2x. What is this? What did we just find here? This is the derivative of the function f at any point x. So if I wanted to find the slope of the tangent line at, let's actually do one. Let's find the slope of the tangent line at x equals 4. All I would have to do to find the slope of the tangent line is take my derivative and plug in the x value. So that would be 2 times 4, or 8. So you don't have to do the whole difference quotient for every single point if you find it in general. Then you just plug in your point and you have your slope of your tangent line anywhere you need it, or the derivative any point you need it. All right? So here's our second question, our second example. It says differentiate this function using the definition. What does it mean by definition? Sometimes it just says the definition of the derivative, sometimes it says the difference quotient. So both of those mean the same thing, that formula we were just talking about. So if you're taking calculus this semester and you've seen this before, remember, you can't just give me the derivative, especially on a limit test. You have to use the limit definition. That's another way, sorry, that's what I meant here, limit definition, to find the derivative for the first test, definition. So let me do another one. So if we're going to find the derivative of this function using the limit definition, we're going to take the limit as h goes to 0, copy your formula down. That's the best way to memorize it, is to write it every time, all over h. So again, I'm going to do the work on the side to find f of x plus h. This time you're going to find that it's not really much work to do. You just plug x plus h in where the x is, x plus h minus 5, and you can't simplify that, so you're kind of stuck. So let's work on our difference quotient then, and see if we can do any work once we have everything plugged in. So f of x plus h is what we just found, 1 over x plus h minus 5, minus the f of x, the original function, so 1 over x minus 5, all over h. So at this point, well, you're taking a limit. You could try to plug in 0. You're going to get 0 over 0, so you've got to do some algebra here. What algebra can we do to simplify this in hopes that we get rid of that indeterminate form situation? Well, I look at this and I see fractions inside of fractions. That's a great algebra thing. We can totally get rid of that. So how do we do that? How do we get rid of the situation where we have little fractions on top of a bigger fraction? There's a couple different ways to do it. I prefer to do the LCD method. I like to multiply top and bottom of the big fraction by the LCD. In this case, that would be the x plus h minus 5 and the x minus 5. These are two different factors. They are not connected in any way, so you have to write both of them. So x plus h minus 5 and x minus 5. If I multiply the top by this, I'm going to get rid of these extra denominators. Don't forget you're multiplying this by the numerators. Whatever you do to the top, you have to also do to the bottom. Like I said, there's other ways to approach this, so if you want to try a different method, you feel free. The limit as h goes to 0. Alright, so we're going to distribute this crazy mess to each of these fractions. So in the first fraction, we're going to cancel out the x plus h minus 5s. Don't actually cancel it because you're going to need to multiply it by the second fraction. So x plus h minus 5s cancel. So what survives is just the x minus 5. So that's the first fraction. That's all that survives. When you multiply your LCD times the second fraction, the x minus 5s are going to cancel. So you're going to end up with x plus h minus 5 left. In between your two fractions, remember you had a minus sign. So that definitely simplified the numerator. On the bottom, well, nothing really happens. You just put it all down there. Nothing can cancel, nothing can simplify in this problem, so we're just going to leave it. So on top, the parentheses for this first one, they aren't doing anything, so you can drop those parentheses. It won't change anything. The second one, the parentheses are very important because it's saying all of this has to change its signs, which means these x's are going to cancel each other out, and these negative 5s will be negative 5 minus a negative 5. They're going to cancel. So what survives? Don't forget your limit notation. On top, we have a negative h. That's it. Everything else canceled. On the bottom, well, we still have everything because nothing canceled. All right. You can try to take the limit by plugging in 0, but you're going to get indeterminate form, 0 over 0. So let's do some more algebra. What algebra can we do to try and simplify this? Well, we do have an h factored on the bottom and an h on the top, so we can cancel those out. If we cancel everything out on top, remember to put a 1 as a placeholder. So we have the limit as h goes to 0 of a negative 1 over the two parentheses survive. So x plus h minus 5 times x minus 5. Now at this point, I'm not going to get a 0 on top because that's a constant. So on top, we know what the limit is there. Let's try and take the limit of the bottom. So if h goes to 0, this guy right here zeroes out. So we end up with an x minus 5 times an x minus 5. Well, that we can put together and write as x minus 5 squared. Notice right here, I got rid of my limit notation because I let h go to 0, the limit is gone. So at that point, limit's gone. This is our answer. What did we find here? Remember, we were looking for the derivative. So this is the derivative of f at any point x. Plug in whatever x you want, and you're going to find the slope of the tangent line at that point. All right. These take a lot of practice because there's a lot of different algebra tricks that you might find. So it's very important that you do your homework and make sure you understand it. Each one is probably going to have a different little algebra trick. Like this one, we had to use the LCD to get rid of fractions inside of fractions. All right, let me bring up. All right, this is our third example. This one looks like fun. So again, we're being asked to use the definition. So this is the limit definition. So the limit as h goes to 0 of f of x plus h minus f of x all over h. Now looking at this, if I plug x plus h in, there's not going to be any simplification that I can do. So I'm just going to go ahead and plug it straight into my formula. So limit as h goes to 0, f of x plus h. So by square root, I'm going to plug in x plus h where the x was. Don't forget that 1. That has to stay there. Minus the original function, the square root of x plus 1. All of this is divided by h. That looks like so much fun. We're going to have a great time here. All right, so this is something that we have already talked about, a trick that we're going to use here. When you have square roots with two terms, they don't both have to be square root terms. In this case, they are, which makes it more fun. You're going to use the conjugate to try and simplify. Oh, back up. First of all, if you plug in 0, you get 0 over 0. That's why we're moving on to algebra. So the algebra trick that we're going to use is conjugates again. So remember, when you do conjugates, it's the term in the middle that you change between the terms, or the sign between the terms. So we have x plus h plus 1 plus the square root of x plus 1. We're conjugating the top to try and get the square roots to disappear. Whatever you do to the top, you have to do the same thing to the bottom. You conjugate the one with the square roots, and then you put the conjugate on top and bottom. All right, we have the limit as h goes to 0. What happens when you multiply conjugates? You use the FOIL method, but conjugates, the middle terms always cancel. So if we multiply first terms here, square root, times itself. Well, the square root disappears. We end up with x plus h plus 1. Square root's gone. If we multiply the last terms, a negative and a positive make a negative, then square root times itself, we just end up with what's inside. Make sure you put the parentheses for that second one because it's minus everything in the parentheses. On the bottom, you could distribute the h if you wanted to, but it's not going to simplify. Kind of look ahead and see where it's going. It's just going to make a bigger mess. So I would leave it factored in hopes that we can reduce while we're in the factored form. So I'm just going to copy the conjugate down to the bottom. And let's see what we can do. You could try and take the limit, let h go to 0, but it looks like we have some algebra we can do on top. If we look at it, we have x minus x. They cancel. 1 minus 1. They cancel. So what survives on top? Limit as h goes to 0. We have a positive h this time over, we have a positive h on the bottom, and then we have this disaster, the conjugate. So we can try and plug in, but we get 0 over 0, so we gotta do algebra. The h's cancel. If you cancel everything on top, what do you have to put? A 1. All right, let's look at this. Now, I could write it and clean it up, but I want you guys to understand that you can skip some steps. So at this point, if we let h go to 0, that means this guy right here is going to go to 0. Well, let's write what we have left. Let's just take the limit right there. 1 over, because it's not indeterminate form, so we have a 1 on top. On the bottom, we have the square root of x plus 1. Plus the square root of x plus 1. How do you add square roots together? You add the numbers in front. this case, they're 1s. So 1 over 1 and 1 make 2 square roots of x plus 1. And there you have it. What did we find here? This is the derivative of the function f that we were given. So those are 3 great examples, 3 different levels, 3 different algebra routes you're going to need. Now, one more thing to show you. In all 3 of the examples we just looked at, we use this notation f prime of x to denote the first derivative. If you look at this list, there are a whole bunch of ways we can denote a derivative. Y prime is a very popular way to do this, and that's perfectly fine. Just be very careful that it's a prime and not a 1. I would prefer the f prime of x notation over the y prime, but you're going to find sometimes where y prime is easier for you to keep track of. Just make sure you don't lose that prime in the process. Another way to denote a derivative is called dy dx. It stands for the derivative of y with respect to x. This is going to be something that we use a lot. He's going to be very useful when we do our applications, our word problems, and it's also going to come up a lot in implicit differentiation. You'll see. If we're talking about a function f, which is the same as y, we can replace the y with f. So this is the derivative of f with respect to x. The one right here, so all they've done is they've separated it out. This is literally saying, take the derivative with respect to x of this function that comes next. So this is like an operator. It's telling you what to do to what comes next. So d dx means take the derivative of the next piece, whatever it is. These notations we aren't going to use in this class, but you'll probably see them later on in Calc 3 and differential equations maybe, I don't remember. But definitely Calc 3 you'll see those capital D's, they come up. Alright, that's my discussion for this video. Practice makes perfect. Make sure you study hard, and I'll see you in the next video.